Assalamualaikum and hello everyone. Today my team from group 1 are going to present about the eddy current dynamometer. The subject is BMMF 2114 Vehicle Performance Analysis. Next, my team member. Me, Idris bin Azman, Qayyum bin Abdul Wahab, HERMAN bin JOANNES, and lastly AHMAD DANIAL bin AHMAD RAFI. Next, introduction. An eddy current dynamometer is a device that measures and controls torque and rotational speed in a variety of applications. It works on the principles of electromagnetic and uses the phenomena of eddy currents to produce resistance and correctly measure torque. Next, auto testing engine development and industrial machinery intensively use eddy current dynamometers. They are critical in determining the performance, efficiency, and durability of engines and other spinning machinery. Next, the interaction of a magnetic field with conductive material is the basic concept behind the operation of an eddy current dynamometer. When a revolving metallic disc or drum, known as the rotor, is put within the magnetic field created by a series of stationary electromagnets, it produces circulating electrical currents, known as eddy currents, in the rotor's conductive material. Next, these eddy currents provide a resistive force that resists the rotor's speed, resulting in braking. The intensity of the eddy currents and consequently the degree of resistance provided to the rotor are determined by the strength of the magnetic field and the speed of rotation. Next, the torque assisted to the rotor may be reliably evaluated by measuring the electrical power necessary to maintain a consistent speed of rotation against the resistive force. This torque measurement is critical for evaluating engine performance and efficiency, as well as conductive numerous tests and studies. Next, eddy current dynamometers provide a number of advantages. They have a high torque capability and can carry heavy loads. They have quick reaction times, making them appropriate for dynamic testing settings. They can also function at high speeds, making them suitable for a broad range of applications. Next, advanced control mechanisms are built into modern eddy current dynamometers, allowing for exact adjustment of the resistance delivered to the rotor. This capacity allows for the modeling of varied load circumstances as well as correct characterization of engines and machines under diverse operating scenarios. Next, in summary, eddy current dynamometers are electromechanical devices that measure torque and regulate rotational speed by interacting with a magnetic field and eddy currents. They are essential in the testing and development of engines and rotating machinery because they provide precise and dependable torque measuring capabilities. Next is history. The eddy current dynamometer has a long history dating back to the late 19th and early 20th century. It incorporates the achievement of various inventors and engineers who made substantial advances in understanding and applying eddy current principles to torque measurement and control. Okay, next, Frederick George Creed, an English electrical engineer, was one of the field's early pioneers. Creed invented the eddy current brake in the late 18th, which used revolving copper discs in a magnetic field. As the discs rotated, eddy currents were generated in the copper, causing resistance and braking effect. This invention was primarily intended for use in railway braking systems. Next, Herman Urey, a Swiss engineer, made significant contribution to the development of the eddy current dynamometer. Building on Creed's work, Urey conceived and built the first practical eddy current dynamometer in 1906. His concept included an electromagnet stator and a rotor constructed of conductive material. When torque was applied to the rotor, eddy currents formed, producing resistive force that could be measured and utilized to calculate torque. Next, Urey During eddy current thermometer improved significantly on prior versions. It provides a more precise and dependable technique for measuring torque, and its small and efficient design made it appropriate for a wide range of applications. During innovations was a watershed moment in the evaluation of eddy current dynamometers. Okay, next, advance in materials, electronics, and engineering approaches during the next few years enhance and increase the capabilities of eddy current thermometers. They are used widely to include car testing, engine development, and industrial machines. Next, modern eddy current thermometers include advanced control systems that enable exact resistance modification, allowing realistic modeling of various load circumstances and dynamic testing scenarios. They enable real-time torque and rotational speed monitoring and control, assisting in the evaluation of engine performance, efficiency, and durability. Lastly, overall, the eddy current thermometer's history is distinguished by the contribution of innovators such as Creed and Dury, who recognized the potential of eddy currents for torque measurement and produced practical devices that revolutionize the disciplines. Continuous technological and mechanical improvement have further expanded the capabilities of eddy current dynamometers, making them vital instruments in a variety of sectors today. Okay, next is system and technology diagram. This is a technology diagram for eddy current dynamometer. Next, the system of an eddy current thermometer consists of several key components that work together to measure and control torque and rotational speed. The main elements of an eddy current thermometer system. Number one, stator. The stator is the stationary part of the dynamometer and typically consists of one or more electromagnets. These electromagnets create a magnetic field within which the rotor operates. Next, rotor. The rotor is the rotating part of the dynamometer is is typically made of conductive materials such as copper or aluminium. It is connected to the rotating shaft whose torque is being measured. As the rotor rotates within the magnetic field generated by the stator, it induces eddy currents within a conducting material. Okay, next, magnetic field control. The magnetic field produced by the stator is controlled to provide the desired level of resistance or braking force. The strength of the magnetic field can be adjusted using various methods, including adjusting the electrical current flowing through the stator's electromagnets. Okay, next, eddy currents. As the rotor rotates within the magnetic field, the changing magnetic field induces eddy currents in the conductive material of the rotor. These eddy currents circulate within the rotor, creating a resistive force that opposes to the rotational motion. The strength of the eddy currents depends on the speed of rotation and the magnetic field strength, which in turn is determined by the stator's electromagnets. Next, torque measurement. The resistive force generated by the eddy currents is directly proportional to the torque being applied to the rotor. This resistive force can be measured using various methods, such as strain gauge, load cells, or electrical sensor. The measured torque provides an indication of the rotational force or power being transmitted through the dynamometer. Okay, next, control and data acquisition. Eddy current dynamometers often include a control system that allows for precise adjustment of the magnetic field, strength, and other parameters. This control system enables real-time control and monitoring of the dynamometer's operation. Data acquisition systems are also employed to capture and analyze the torque, rotational speed, and other relevant parameters during testing or operations. Okay, next, cooling system. Eddy currents dynamometers can generate significant heat during operation due to the resistive force generated by the eddy currents. To dissipate this heat and maintain optimal performance, a cooling system is typically incorporated. This may involve the circulation of coolants such as water or oil through channels or passages within the dynamometer. Lastly, by combining these components, an anti-current dynamometer system can accurately measure torque and rotational speed, provide resistance or load simulation, and offer control and monitoring capabilities for various applications, include engine testing, performance evaluation, and research and development.
Hello, my name is Ahmad bin Ahmad RAFI. I'm from 2BMMF. Next is theory of operation. The operation theory of the eddy current dynamometer is based on the principle of electromagnetic induction. It uses the interaction between a magnetic field and electric current to measure and control the torque and speed of the rotating system. Additionally, the stated electromagnetic creates a magnetic field that surrounds the rotor. These electromagnets are usually assisted by a DC power source of a three-phase AC power supply. Magnetic field lines extend electrically equal toward the rotor. When When the rotor turns in a magnetic field, relative motion is creation between the conductive rotor and magnetic field. Next is torque measurement. Rotor torque can be measured by analyze the electric power required to maintain the magnetic field in the status. The power required to maintain the magnetic field is proportion to the torque resistance by the rotor. This power can be calculated by measuring the electric current and voltage supplies to the status electromagnetic speed control by adjusting the excitation current in the status electromagnetic. The strength of the magnetic field can be controlled. Increase the excitation current, increase the station of the magnetic field, resulting in more damping force and higher torque requirements from the rotor. This allow this allow precise control of the rotation speed of the system under test. Eddy current dynamometer are commonly used in automotive and industry application to test and measure the performance of engines, motor, and the other rotation machinery. They provide a simple and accurate way to apply and measure the load on the system under test. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Qayyum bin Abdul Wahab. I will present about type of experiment on dynamometer. Explain six type of experiment. Okay, the first one, torque measurement experiment. In this experiment, a dynamometer is used to measure the torque output of a rotating system, such as an engine or motor. The dynamometer is connected to the system's output shaft, and as the system operates, the dynamometer measure the torque accepted. This experiment helps in understanding the torque characteristic of the system and its performance under different operating conditions. Okay, second, power measurement experiment. This experiment involves using a dynamometer to measure the power output of a machine or engine. The dynamometer is connected to the system's output shaft, and as the system operates, the dynamometer measures the power generated. Power measurement experiment help in evaluating the efficiency and performance of the system and can be useful for optimizing its design and operation. Third, efficiency testing experiment. In an efficiency testing experiment, a dynamometer is used to measure both the input and output power of machine or engine. By comparing the input power typically supplied by an electric motor with the output power measured by the dynamometer, the overall efficiency of the system can be determined. This experiment helps in assessing the energy efficiency of the system and identifying areas for improvement. Okay, for load testing experiment. Load testing experiment involves subjecting a machine or engine to various load conditions to assess its performance and capability. A dynamometer can be used to simulate different load conditions by applying a controlled resistive force or torque to the system. This experiment helps in evaluating the system's stability response and power output under different load scenarios. 5. Endurance testing experiment. Endurance testing involves subjecting a machine or engine to prolonged operation under specific conditions to evaluate its durability and performance over time. A dynamometer can be used to continually measure and monitor the torque, power, and other parameters of the system during the endurance test. This experiment helps in assessing the system's reliability, identifying potential issues, and estimating its operational lifespan. And the last one, control system evaluation experiment. In this experiment, a dynamometer is used to assess the performance of a control that regulates the operation of machine or engine by applying control load variation or change in operating condition. The dynamometer can simulate real-world scenarios to evaluate the control system responsive, stability, and accuracy. This experiment helps in fine-tuning and optimizing the control algorithm and setting for improved system performance. Okay, that's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Herman bin Joannes, so I will continue this presentation. Advantage and disadvantage of the system. Eddy current dynamometers, also known as electromagnetic dynamometers, offer several advantages in various applications. So here are some of the key advantages of using eddy current dynamometers. The first is high torque control. High torque control is provide precise and accurate control of torque output. The torque can be easily adjusted and controlled through the excitation current, allowing for precise load simulation and testing. Number two is wide torque range, and these dynamometers have a wide operating range, making them suitable for testing a wide range of engines, motors, and other mechanical systems. They can handle both high and low torque applications effectively. And number three is quick and responsive. These eddy current dynamometers offer quick response times due to the nature of the eddy current phenomenon. They can rapidly change torque and adapt to dynamic load conditions, making them ideal for applications that require quick load change or simulation. And next is non-contact and non-intrusive. Non-contact and non-intrusive is eddy current dynamometers operate without any physical contact with the tested system, and the torque is generated through electromagnetic induction, which eliminates the need for mechanical couplings or physical connection. This non-contact operation minimizes the risk of damage to the tested equipment and allow for easy installation. And the last is high power density. Eddy current dynamometers have a high power to weight ratio, making them compact and suitable for application where space is limited. They can handle high power levels while maintaining a relatively small physical footprint. Here are some disadvantages of using eddy current dynamometers. The first is heat generation. Heat generation eddy current dynamometers generate significant amounts of heat during operation. This heat needs to be efficiently dissipated to prevent overheating, which can affect the performance and longevity of the dynamometer. Required cooling systems and heat management strategies are required, adding complexity and cost to the setup. And the second is cooling requirements. Cooling requirements due to the heat generated, eddy current dynamometers often require dedicated cooling system such as water or air cooling to maintain optimal operating temperature. This cooling system add complexity, costs, and maintenance requirements to the dynamometer setup. And the next is cost. Eddy current dynamometers can be relatively expensive compared to other types of dynamometers, such as hydraulic or water brake dynamometers. The initial investment cost may be higher, especially for high power application. The additional cost of cooling system and power consumption should also be considered. And the next is power consumption. Power consumption, eddy current dynamometers require a power source to generate the electromagnetic field. This power consumption adds to the operational costs, especially for extended testing session. The energy efficiency of the dynamometer should be taken into account to optimize power consumptions. And next is torque limitation. While eddy current dynamometers offer a wide torque range, they may have limitation when it comes to extremely high torque application. In such case, alternative dynamometer types like hydraulic dynamometers might be more suitable. And the last is electromagnetic interference. Eddy current dynamometers generate electromagnetic fields during operation, which can potentially interfere with sensitive electronic equipment in the vicinity. Proper shielding and precaution should be taken to minimize electromagnetic interference and ensure accurate measurement. And this is my opinion on the technology for the near future. And this is six type any improvement should be done on the selected technology. The first one is advanced control algorithms. Future eddy current dynamometers may utilize advanced control algorithms to enhance precision and control capabilities. These algorithms could incorporate machine learning and artificial intelligence technique to optimize torque measurement accuracy, adapt to dynamic load condition, and enable more precise control the torque output. The second is integration of advanced sensor. Eddy current dynamometers of the future could be equipped with advanced sensor for the real-time monitoring of various parameters. The sensor could include vibration sensor, temperature sensor, strain gauge, and other measurement device, providing comprehensive insight into the behavior and performance of the tested system. And the next is intelligent diagnostic and predictive maintenance. With the integration of advanced sensor and data analytic capabilities, future eddy current dynamometers may offer intelligent diagnostic and predictive maintenance feature. The dynamometers could continuously analyze the collected data, detect anomalies, and provide predictive insight regarding potential issue and maintenance requirement, allowing for the proactive maintenance and minimizing downtime. The next is improve heat dissipation mechanism. Heat management will remain a focus of future eddy current dynamometer development. Innovative cooling technique such as advanced liquid cooling system or thermoelectric cooling methods, could be employed to enhance heat dissipation and maintain optimal operating temperature. This would ensure prolonged operation without compromising performance and reliability. And next is energy efficient design. As energy efficiency become increasingly important, future eddy current dynamometers may incorporate energy saving feature. This could involve the development of regenerative braking systems that capture and store energy during declaration, or the integration of energy recovery mechanism to minimize power consumption and reduce overall operating costs. And the last is virtual testing and simulation integration. Eddy current dynamometers could be further integrated with digital simulation platforms and virtual testing environment. This integration would allow for visual prototyping and system optimization, enabling engineers to perform extensive testing and analysis before physical prototypes are built. It would streamline the design process, reduce costs, and accelerate time to market. So, in my opinion, for the future of eddy current dynamometer technology, holds great potential for advancement and innovations, and there are types improvements should be done on the selected technology. Thank you.